Okay, this is an introduction to section 14-6, motion relative to a rotating axis. Now, I consider this to be one of the most difficult new concepts to take on in the dynamics class. Uh, it's not necessarily the hardest chapter in the book, but it has quite a steep increase in the learning curve. So don't feel bad if this one takes you a little while to wrap your brain around, or if you feel just incredibly confused. I'm going to do my best to point out the most important concepts and kind of clarify some of the figures and the terms in the equations. What I won't be doing is just the raw derivations, okay? Because I mean, I would just be repeating what is already written in the book, and it's math. It's just true. I don't necessarily feel like that those who are confused about the concepts in this chapter are necessarily needing me to clarify the mathematical steps. I believe that if the math makes sense to you, then that either means that you just know the patterns and the patterns don't really add any new understanding to you, or that you're weak on the math and just pointing out the patterns again may not necessarily be the thing that you need to understand the concepts. All right, so the the things that I feel that at first you may want to really look into are on this page, page 150. There are three descriptions of types of situations where you would care about the motion of an object that is moving relative to a rotating axis. Okay. And I feel like the easiest one to really relate to is this first one that would talk about that you have an object that is moving on Earth. Let's say you're standing, on the sidewalk and you're watching a car go by. And in order to watch the car go by, you're looking to the right. The car's coming from your right, and you slowly turn your head to the left as the car passes you, and then the car moves off in the distance, and you don't really have to turn your head anymore. So that is an example of relative position and relative velocity. And when you are watching the car go past you, your head turns the fastest when the car is going right in front of you, and then your head is the turning of your head slows down more and more as the car gets further and further away. So that phenomenon of your head starting off slow, moving fast, and going slow again is all about relative position, relative angle, and also is showing that the relative velocity of the car, maybe the car never changed speed, but to you, the car was moving at relative to your position. Okay, so now jump into a spaceship and go and hover above the Earth, but don't match the rotation of the Earth. Just watch the Earth rotate, and then this is a little bit strange, but watch that car driving down the road again. It's the same car on the same road going the same speed, but now you're pulled away very, very far. So you see this car driving down the straight road, but you also have to take into account that now the Earth is rotating from your perspective. So the path of the car will not be a straight line anymore. In fact, this car that was going straight down a road, let's say I have my road, and then I'll just make like a red car that's going straight, is now on an Earth that is rotating. So now the Earth, I'll say the green arrow is the Earth's rotation. So the car is sliding sideways. And so this isn't exactly how the chapter is set up, but the concept is there. So the car we'll start in this position here. We'll move down, but also the green line, the green motion will cause it to pull to the right. So you'll start here and then the car will kind of come out like this. There may be a bit of a curve or something like that, right? So it depends on how quickly the earth is spinning compared to how quickly the car is moving and if the car changes speed. But you might get a curve, something like this, or it'll just stretch the line out at an angle. Okay, so basically you're adding the motion of the car relative to the earth on top of the earth's movement also. And if you think of this as a three-dimensional case, then the earth is actually curved too, so the car kind of pulls away from you as it goes around the corner, all right, from away from you from your perspective. So there are things to take into consideration when it comes to those kinds of concepts. Okay, next is point 2. It says the motions of 2 points are somehow related but are not equal and are not on the same rigid body. For example, some mechanisms are connected by pins that slide in grooves or slots. Okay, that is basically what they're talking about in the figure down below. Okay, down here where there's we got this object that's rotating about point A, and then we've got this pin that goes up and down in this slot. All right, so that means that not only will the pin be rotating, let me clean this up a bit, but the pin will also move in the slot as well. So there'll be a rotational motion for the pin and then an upward rotation, or not a rotation, but an upward movement of the pin as the object that it is encompassed is rotating as well. So you have two types of motions going on, but you're tracking only this object as if you don't care about the other object's motions. The other object is creating these motions, but you have to try and imagine only looking at this pin. What if you could only look at the motion of that pin and not see the slot that the pin was in, and try to explain why the pin might be moving up and over? Okay, so that's what I'm imagining, is the pin might do this kind of curved motion that's more amplified than just the curve of the slot that it is inside, right? So this kind of motion is closer to the kind of problems that are set up for us in the back of the chapter. Some sort of a mechanism, an arbitrary mechanism that has two different motions that are adding on to each other. Okay, number 3, the solution of kinetic problems involving the rotation of irregularly shaped rigid bodies. Moments and products of inertia depend on the coordinate system used to describe them. If the axes are fixed, but the body rotates, then the moment of inertia will change unless the body has certain symmetries. Okay, basically they're saying, like, you have an object, and then so basically saying that you have an object, but maybe this object is more dense on this half, and then more sparsely dense down here. And so the object's center of mass will be kind of, let me change the color a little bit, like centered there, but you're trying to rotate the object at this location, and that causes the weight of the object to be kind of off to the side, and it kind of does like an interesting motion, or it kind of bobs around or something. Okay, so the moment of inertia and the way that the object rotates can basically have a strange path that can be explained in a way of talking about an object rotating, but then also having some sort of a strange translational change in position. Okay, so to me, the first example in this is the more relevant if you're interested in space travel, or maybe even travel in water where there's a current or something like that. Number 2 is for mechanical systems, machinery and things like that sort. And then number 3 kind of again would go back into, say, space travel, or maybe some sort of kinematics, I don't know, weight training or something like that, where you have to deal with the motion of weighted objects, or non-uniformly dense objects. Okay, now 14-6, section 0.1, position. So this is going to introduce us a little bit to the idea of there being some new terms in the position and relative position equations to think about. So they highlight the R vectors, the position vectors. And they've changed the symbology a tiny bit. So this isn't any different than what we have been dealing with before, that there is an I hat and J hat component to our position. However, notice that the X and Y values are now capitalized. That is to distinguish the difference between the axis that is fixed from the axis that is rotating, okay, which is what I am highlighting in red, okay? So the lowercase x and y axis is locked to the rotating disk. The capitalized x and y axis is locked to the stationary ground. Now, the ground doesn't always have to be the stationary thing. It's whatever your frame of reference is going to be. And then there will be something rotating relative to that frame of reference. And then there will be, and I will highlight this in green, another thing moving relative to the rotating frame. That's what this chapter is about. All right. So the orange axis is fixed, the red axis is rotating, and the green circled object is moving relative to the rotating axis. We are going to make sense of the math that will tell us how the object in green is moving, since it is being influenced by the rotating object that is being related to the fixed axis. Okay, so there's 2 layers of motion going on here with a third fixed frame of reference. So how do we distinguish? Well, first, we want to understand that there are going to be positions that are relative to the fixed axis. Next, there are positions that are relative to the rotating axis. So they're changing the terms a little bit as far as the position of B relative to A term in the equation. Now the position of B relative to A has something to do with the axis that's rotating. Okay, so they say here in the description below equation C, I guess it's 1410C, this is the equation I'm talking about, that where the unit vectors along the rotating axis x and y, the rotating x and y axes, have been denoted as e hat sub x and e hat sub y to distinguish them from the fixed unit vectors I hat and j hat. So these are the I hat and j hats that are rotating. So if we go back to the previous page, these directions here are the EX and EY vectors. They are the rotating axis that is relative to the fixed axis. Okay, so that is giving us a slightly different B relative to A term. And then they highlight, and we'll see this in the problems, that you can get these values by using the cosine theta, sine theta, and negative sine theta and cosine theta values. So the axis position relative to the I hat j hat, this is the conversion, okay? And then the I hat and j hat conversion for the y-axis, the rotating y-axis, is the negative sine theta I hat plus the cosine theta j hat. This will make more sense once you see it in action, okay? So right now, this is just kind of a, the math works out press the I believe button, and when you see it in action, hopefully it will click a little bit more. But I just want you to be aware of these conversions. Okay, so section point 2, velocity. And then we have acceleration. I hope that that's not a surprise. Okay, so velocity is going to take our b relative to a term. Now, right here, this is just our velocity of b relative to a. In the original equation, the velocity of b is equal to the velocity of a plus the velocity of b relative to a. We've been using this in the problems. But now, this b relative to a part of the equation is not so straightforward, all right? Because our position of b relative to a, when we take the derivative, is not the same function. Now, there is the version that was above right here. This is our b relative to a position. Now, if we take the derivative of b relative to a with this new form, we actually have to use the product rule, and we get a slightly different result. So this is the result of the derivative of b relative to a over dt, all right? Now, in the end, what happens? We end up with a velocity of b relative term, and then this x d e sub x d over dt and y d e sub y over dt. Now, where did this come from? Well, if you do the product rule yourself, then hopefully it is pretty straightforward that you know that you're going to get these two terms. And those two terms are what's being carried over to this part of the equation. Okay, so that means that what's left over, this dy over dt ey and this dx over dt ex, must be turning into this velocity of b relative. All right, well, let's look at the explanation down below. That the velocity of b relative is equal to x dot e sub x plus y dot e sub y, and is the velocity of b relative to the rotating xy coordinate system. Okay, so this is the movement of that pin in the slot relative to the rotating disk. All right, it says that is the velocity of b relative to the rotating xy coordinate system. So if we go back to the previous page, see how the diagram has velocity of b relative as a straight line coming off of that pin B. And pin B can only move up the slot tangent to this curved slot. So at this instantaneous moment, you will have a tangential velocity vector. And that's all this is. It's just that velocity written in that direction, and it has a vector value. But that vector value is being written relative to this rotating xy axis, okay? Because that's how we know that the arrow is tangential to the slot. And as the slot rotates, that tangent will continue to rotate with the slot, or with the object. All right, so we just have to understand what these terms are actually describing to us. So if we go back then, and we know that that is the definition of velocity b relative, and these derived terms turn into velocity b relative down there, then all we need to do is make sense of some of these other terms, these last two terms, the x times d e sub x dt and y times d e sub y dt. Well, without going too deep into the derivation, which I feel like you can look back and realize that there's like the chain rule, skip some steps, but this is the punchline to the Y version. The X version was just before this on the previous page. And then the definition of a derivative, that basically you end up with this final chunk in the Y. And if you go back, you have the final version in the X as well. So it's the same process in the X. And then again, I just highlighted that process in the Y. So what does that do for us? Well, look at the final version of the equation. All right here. We have the velocity of B is equal to velocity A. I'm looking at the second line, plus the angular velocity crossed with the position of B relative to A, plus the velocity of B relative to the rotating axis. Okay, that's a mouthful, but there really is not much extra going on as long as you understand that there is basically a term that we used to have, which was that velocity A plus velocity of B relative to A. The velocity of B, it's kind of, maybe that's a little tough to read, but the velocity of B relative to A is this piece with the fact that the axis is rotating. The motion of B relative to A has a rotational component now because that object sliding or translating relative to A is also on a rotating object. All right. So that's what this extra term is illustrating, is that still B relative to A, just with an extra little spin to it, pun intended. All right. Now, what do we do with this? Well, think about what cross product is. Right? Yeah, this requires a little visual imagination, and I'll try my best to illustrate it on the screen here. If we have omega, that is a rotation. All right, but if we're talking two dimensions, and I typically try to stay in two dimensions because this class is already difficult as it is, that for us to go into three dimensions right away just makes it even more daunting. But if this object is rotating in the two-dimensional plane on the screen, then the axis of rotation is this dot pointing out of the screen. Okay, so remember, an object is rotating around in the 2D plane, but the axis, the line that it's rotating around is coming out of the screen. And out of the screen is that thing that I can't motion to you because this is a video and you're watching, you can't even see me visually. I don't have my camera going, but even then that doesn't help too much more. So I need to rely on you to understand that this dot is a line coming out of your screen. So that means it's in the k-hat direction. Okay, and then the direction, or sorry, the position of B relative to A is always going to be A is somewhere and B is somewhere else. Okay, so there's going to be some vector coming in the going along the plane. So let me change the color on that, and let me circle that vector here, this position of B relative to A. It's going to be this blue vector. So if we know that the rotation vector is k-hat coming out of the screen, and then we have some position of B relative to A that is in the plane, that's along the plane, then we have a 90-degree angle in three dimensions, right? Remember, again, I can't motion with my hands. This isn't face-to-face. This is on a video. The vector, the k-hat vector is coming out of the screen, and then it doesn't matter which direction this other vector is going. It will be perpendicular to the k-hat vector. Cross products give you a value that is perpendicular to both. So perpendicular to a vector coming straight out of the screen and perpendicular to a vector that goes from A to B is going to be another vector going in this direction or going in that direction. right? Depending on the sign of the k-hat, okay, if we're going out of the screen or directly into the screen. Okay, it will depend on which version of this blue arrow we have. And you use right-hand rule to determine the sign, right? But that's exactly how a cross product works. And that's the kind of vector we're getting. So if we know there's a rotation and we know that the blue arrow is AB, right, then you're going to get another vector in green that is going to be perpendicular to both. So what does that tell us? That is the motion. That's the motion in that direction. Okay, and then you're going to add the motion of velocity b relative to the rotating axis. All right, so these two velocity terms are being added together, and it's going to be the final motion of the object as it's sliding along the rotating object, and the object rotates with it or forces it to rotate along. All right, sorry, I used it too much in that one, but it the two terms are adding up so that you have what is in this diagram. You have your omega and you have your vector of b relative to a, which is being cross product. So there is an axis of rotation right here. Let me change the color, make it a little more bold. This is your k hat omega, and then that green vector that I had drawn just a second ago, and I'm going to redraw that green vector, is the position vector b relative to a. And so what is perpendicular to both those vectors? The vector that I'm circling right here. Okay, that vector is the omega cross rb relative to a. Right? It's the velocity crossed with the position. And that is a motion. That is how the pin is being moved by the rotation of the disc if the pin wasn't sliding in the disc. If the pin stayed in the location that the pin is locked into the slot, if the pin did not move in the slot, then the rotation of the disc would cause the pin to move in the vector that I have circled in green. And that is the cross product. Then the pin is also moving relative to the rotating object. That is the velocity of b relative. You add those two motions together, and then you're going to get some sort of like curvy, weird motion, okay? That's what we are calculating as the new b relative to a term when you have a rotating axis. That is what this new piece is. Okay, acceleration, section 0.3. This is kind of the same story, but just like with the relative velocity and relative accelerations, where the acceleration had two terms, I'll refresh your memory on that. This one is also going to have some extra issues as far as having extra terms. All right, so let me kind of just cut to the chase here and show you the final equation and point out first that this final equation is not two parts. This is the whole thing. All right, so that's probably a little bit like, oof, okay. And so, but you still have the same beginning of the story. The acceleration of b equals the acceleration of a plus the acceleration of b relative to a. You know, kind of the story that we've been dealing with in the past, okay? But now there's all this mess. All right? So, how do we make sense of all of this mess? Well, one thing is that we can work backwards a little bit here. Let me cut to the end of the story. Well, one of the end of the stories is this term, the Coriolis acceleration, which is just this final term, okay? So the it says here, the remaining term called the Coriolis acceleration has no simple interpretation. That's a bummer. As indicated by the vector cross product, the Coriolis acceleration will always be perpendicular to both omega, it will be in the plane of motion, and the velocity be relative. It will be perpendicular to the slot along which the pins travel. All right, so Coriolis acceleration is a tough concept to understand and interpret, but do at least see that it is kind of the acceleration version of the omega, oops, not drawing, the omega cross the position of B relative to A. Remember from the velocity? That's not exactly how the term works, but it's really actually just B slash A, B relative to that, B relative to A. So I wrote that wrong, but it is a similar final term, okay? So if we know the omega has a k hat direction, and we're crossed with a VB relative, which we already know from that example in the figure a few pages back, that the pin's motion is the motion of the pin relative to the rotating disk. And if we know the disk rotation, then it is k hat. So remember, this red dot is coming out of the screen. Then there's going to be some perpendicular vector, right? But this vector is now going to be an acceleration, right? So it's omega cross velocity instead of omega cross position, right? So mathematically, hopefully that makes sense, right? As far as its functional interpretation, it's just like they said, there is no simple interpretation. And I do remember taking a 300 level physics class that we spent probably 2 weeks just on Coriolis effect and how the physics of calculating the Coriolis actually works and trying to really wrap our brain around it. It is not an easy concept to understand. So at this point, I basically ask for you to understand the math, watch it in action, and use the example problems to try and kind of get what is going on with that term through practical experience through the problems, okay? And then we have the alpha B relative. So not alpha, sorry, the acceleration of B relative. Alpha is not a rotation, it's a linear acceleration. So the term A B relative is the additional acceleration point B has because of its motion along the slot. All right, so if the pin in the slot, so we have that slot in the figure and we've got the pin. If the pin is accelerating, then this is just the acceleration that is tangent to the curve of the pin, or the curve of the slot. Okay. All right. So hopefully those last two terms, well, one mathematically and the other one just kind of are straightforward. You understand that there's if the pin is accelerating, it's going to accelerate in the direction that the slot allows. All right. Now, what is going on here? All right. So we've got two cross products, and one of the cross products actually has two cross products inside of it. All right. It's the acceleration point B would have if it were attached to the rigid body rather than moving relative to it. So this is the acceleration of the object rotating in the disk, but not moving through the slot. Then the last two terms are the accelerations that are due to the fact that it would be moving in the slot while the slot is rotating. All right. So first half of the equation is motion of the rotating disk, and the second half is the acceleration. And sorry, I shouldn't really just say motion, the acceleration of the rotating disk. And then the second chunk is the acceleration within the rotating disk. All right, now let's look at the cross products and see if we can kind of get a little bit of an idea what's going on. So you have alpha is your rotating acceleration. All right, so if the disk is spinning, but accelerating in 2D, that means that this is a k-hat, and then crossed with the position vector. This shouldn't look too much different than when we had r alpha and r omega squared for our relative velocity equations. Okay, so let me just point that out again. So we have the acceleration of b from the previous sections plus equals the acceleration of a plus the acceleration of b relative to a, but the acceleration of b relative to a had two terms. That had the normal acceleration and the tangential acceleration, right? Okay, well then the normal acceleration, if you had the relative acceleration diagram, was the r alpha, and then you had, oh, sorry, that's not, no, this is the r alpha. And then the normal acceleration was the r omega squared. That's what these are. It's just that we're doing the raw cross product versions of this. Okay, so we knew that the rotation had a particular property, and now we're doing the rotations a little bit more brute force method where we have the cross products. Right? So now if you look at the first cross product, the alpha cross with position, well, if A is down here and B is up here, then our position vector is in the plane in some direction, and then the alpha is in the k-hat direction again. So therefore, you'll end up with some vector, some acceleration vector, and off in this direction, kind of up and to the left. Okay, and then we add a cross product term, but order of operations matters. So that's why omega cross r is inside the parentheses. We have to do that cross product first. So let me change colors so we can keep track of what I'm working on here. All right, let me get rid of some clutter and let me work out this. So omega cross r of b relative to a. Okay, maybe this isn't the best color. Let's do blue. All right, so if we know again that omega is in a k-hat direction and r is in some arbitrary direction, then we'll end up with a k-hat and an r, and that will result in some vector as our answer. So now let me draw my vector in a new color. So this vector is the answer to r, or omega cross r. Then we take that answer and we do omega cross our answer. So whatever our vector answer happens to be. Well, this is another, so this omega is another k-hat. So then we're going to end up with a value that's going to be crossed. And let's make that color purple. And it's going to give us another right-hand rule answer. Okay, so practicing like with the right-hand rule, but basically, if my thumb is the k-hat direction, if I take my right hand, my index finger is pointed in the direction of the orange arrow, then the purple arrow is my middle finger pointed down at the left. So this final purple vector is the answer to this entire cross product, and it is an acceleration. So the alpha cross r was here, resulting in an acceleration that went into this perpendicular direction. And then the omega cross r crossed omega is this vector, and it is pointed in a perpendicular direction. So it results in an acceleration, two accelerations that are perpendicular to each other. Okay, but they add up. They may have different magnitudes and things like that. All right, so hopefully mathematically, you're kind of seeing that the rotation, the acceleration of the rotation causes these two terms, and the object accelerating inside the rotating object are the other two terms.